Welcome back to our lecture series on automated machine learning. We are still in the age of foundation models, and today we're really talking about foundation models, specifically tabular foundation models. So far, traditionally, we train one model for one task on a given data sets, and therefore we need to find the best parameter settings, architectures, and so on over and over again. But what if we could actually avoid doing that? And that's the main idea of foundation models. We pre-train a tabular foundation model once, maybe very expensively, but then using it directly for in-context learning on a new data set. We're directly feeding in all our training data and the test data we would like the prediction at once into our foundation model, and directly without training, we're getting our predictions. We focus here in that video on TabPFN because I believe it's the most famous tabular foundation models as of beginning 2026. But nevertheless, there are other very well-performing, maybe even better performing, I don't know exactly, foundation models like Tabular or TabDBT. Let's directly jump into it. What is TabPFN doing? The overall idea is for many models the same. We're saying that we have training data. For these kind of training data, we know, of course, the labels. For our test data, we don't know that, but actually it's a synthetic data set what we're doing for pre-training. I will tell you in a second how to do that data, synthetic data generation. So therefore, of course, we also know the test data, test labels. So we're feeding more that part into TabPFN, which is a neural network, the transformer architecture, which is parameterized by many, by weights, theta. We get in predictions out of that, and then with the help of the test labels, we can now, of course, compute the training loss and know how to optimize our weights of our tabular foundation models in the direction of getting better. And the nice thing is, since we're doing that on synthetic data, we can do it across millions of data sets, hoping that by feeding in more and more data sets with variations and so on, that our foundations model will get better and better. How to do it specifically, here is more the summary idea of that. So first of all, we need some kind of underlying parameters of the dataset we would like to generate. For example, the number of data points, features, nodes, and so on. And then we're saying we also have a graph, an overall graph, which is telling us how data is now more transformed to get to the final generated synthetic data set. So you can see more of the same structure here and here too. And more or less for each generated sample, we propagate the initial data through that graph. So we have some kind of, I don't know, randomly or to some, I don't know, distribution sampled generated data. Let's say we have more or less 3 features here. And we sample random features at the point F and target node positions at that point and read off data at these positions actually. So, and in all of these, we might doing some kind of transformations or connections and how everything is transformed in this kind of computational graph structure. Could also involve some kind of post-processing quantization warping at the very end. But the important point is here, with these kind of graphs, we can simulate neural networks actually. We can have more a tree structure. Then we have more this kind of splitting kind of data, axis aligned, or we can also do discretization actually along this computational graph. And that graph is sampled as part of that beginning, and then data is fed through, and we can get data, synthetic data, to some kind of properties out of that, and doing that over and over again. And we're seeing here, for example, then a data set with 3 dimensions and how everything belongs to 3 input features and how they belong to each other with 2 different classes, or it could also look like that. Nice thing is, doing it often and under this kind of assumption how to sample, that it should be somehow similar to real-world data set. For predictions now, we're doing more of the same, but we don't have, of course, the test labels. We would like to get these. So simply feeding that in and getting predictions over that. How that looks like is more like that. We really that is X train, that's Y train, that's for example X test, and we would like to get that kind of entry. And you can see that always as nodes here. And we have to think about actually how the attention between these nodes is done. For example, we would like to that all features attend to each other, right? So like you have text and say, okay, each token in your text give meaning to other tokens. You do that more as the same on X train and X test. But of course, only in one direction it goes to the label. Always from the features to the label, we have then the attention mechanism only one way. Combining that with an MLP embedding and then with a piecewise constant Riemann distribution, we can get the predicted Y distribution, where we can then sample from and say, okay, what is most likely our output for a given data point. To sum that up, foundation models show or allowed to use a single model for many different data sets. Of course, they are here limited to tabular data sets, but there are similar similar foundation models for example, time series data. To name one of them, it's Kronos. But there are also other things. And it follows a similar idea, more or less like large language models, which are text foundation models, right? It's crucial here to think about synthetic data, right? If you think about large language models, it's always data from the internet or from books or whatsoever. Here it's purely synthetic data, which helps us to resemble real-world data by sampling millions of these, but in a structured way on these kind of causal graphs with some kind of properties behind that. And then we can use in-context learning to feed in an entire dataset, training and test at the same time, and obtain test predictions with that. With that, I hope you have a new perspective on how to leverage transformer models as foundation models to go in one step from a dataset to predictions without additional training. I hope to see you in the next video.